Hello, dear listener, and welcome. As you settle down, perhaps in a soft chair, or nestled warmly in your bed, let us embark on a quiet journey together. A journey not through earthly landscapes, but into the profound, tranquil depths of our universe. Tonight, we will whisper about structures of unimaginable scale and subtle power, structures known as galaxy clusters. Imagine, if you will, the quiet vastness of space. Not the empty void, but an intricate tapestry woven with light and shadow, matter and mystery. Within this immense tapestry, we find galaxies, those majestic islands of stars, dust, and gas, each a universe unto itself. Our own Milky Way is but one such galaxy, home to billions upon billions of suns, each a potential beacon of life and warmth. Now, extend your imagination further. Picture not just one galaxy, but hundreds, perhaps even thousands, of these stellar islands. Imagine them not scattered randomly, but gathered together, held in a silent, cosmic embrace. This, my friend, is a galaxy cluster. A magnificent congregation, a cosmic city, where galaxies are the glowing architectural wonders. These clusters are bound together by an invisible, yet overwhelmingly powerful, force, gravity. Gravity, that gentle, persistent pull that keeps our feet on the ground, that holds our Earth in orbit around the Sun, and our Sun in its grand dance around the Milky Way's core. On the grandest scales, it is gravity that weaves the very fabric of the cosmos, shaping it into the magnificent structures we are contemplating tonight. A galaxy cluster is a testament to gravity's enduring power, its ability to draw together not just stars, but entire galaxies, into a single, cohesive entity. The sheer scale of these clusters is something to truly ponder in the quiet of the night. We're talking about structures with masses ranging from 10 to the power of 14 to 10 to the power of 15 solar masses. To put that into perspective, imagine our Sun, a star of immense brilliance and gravity, multiplied by 100 trillion, or even 1,000 trillion times. This incredible mass isn't just from the visible light of the galaxies themselves, oh no. As we shall gently explore, much of this mass comes from far more mysterious components. For a long time, these galaxy clusters were considered the largest known gravitationally bound structures in our universe. Imagine the awe of astronomers, looking out into the cosmos and seeing these colossal gatherings, believing them to be the very pinnacle of cosmic architecture. It speaks to our human journey of discovery, our continuous quest to understand our place, and the place of all things, within this vastness. Then, in the 1980s, the universe, ever full of surprises, unveiled something even grander: superclusters. These superclusters are the aggregates of not just galaxies, but of galaxy groups and galaxy clusters themselves. So, the clusters we are contemplating tonight are like the major cities, while superclusters are the vast nations, comprising many such cities and smaller towns. It's a beautiful hierarchy, isn't it? From individual stars to solar systems, to galaxy groups, then to galaxy clusters, and finally to superclusters. Each layer building upon the last, a testament to the organizational principles of the cosmos, guided by the silent hand of gravity. Small gatherings of galaxies are often referred to as galaxy groups. These are intimate gatherings, perhaps just a few dozen galaxies dancing together. But when we speak of clusters, we are envisioning something far grander, far more populous. Let us now delve a little deeper into the fundamental nature of these cosmic behemoths. What are their basic properties? What defines them? Picture, if you will, a collection of anywhere from 100 to 1,000 individual galaxies. Each a spiral, an ellipse, or an irregular whisper of starlight, all contained within a single cosmic boundary. But these galaxies, shimmering with the light of their stars, are ONL. Why part of the story? Within the vast expanse of a galaxy cluster, you'll also find incredibly hot, X-ray emitting gas. Imagine an invisible ocean of superheated plasma, stretching across millions of light years, bathing the galaxies within it in its silent glow. And then, there is the most enigmatic component of all, immense amounts of dark matter. This unseen, undetectable substance, a profound mystery, constitutes the vast majority of a cluster's mass, silently dictating its structure and destiny. These clusters typically possess total masses ranging, as we gently noted, from 10 to the power of 14 to 10 to the power of 15 solar masses. This immense gravitational weight creates a profound well, a cosmic depression in spacetime, holding everything within its grasp. The sheer scale is difficult to grasp, but perhaps envisioning 1,000 trillion suns, compressed into a region of space, might offer a small glimpse. In terms of their physical dimensions, these clusters are truly colossal. They typically stretch across diameters of 1 to 5 megaparsecs. To give you a sense of this distance, 1 megaparsec is roughly 3.26 million light-years. So, we're talking about structures that are anywhere from 3 million to 16 million light-years across. Imagine traveling at the speed of light, the fastest possible speed in the universe, and it would still take you millions of years to traverse from one side of a cluster to the other. Yet, within this immense span, the individual galaxies themselves are in motion, each performing its own majestic dance. The spread of velocities for these individual galaxies, as they orbit within the cluster's gravitational embrace, is quite considerable, often ranging from about 800 to 1,000 kilometers per second. So, while the cluster itself is a vast, stable entity, its constituents are moving with incredible speed, a silent ballet choreographed by gravity. Let us now gently uncover the true composition of these cosmic wonders. As we noted, a galaxy cluster comprises three main components, each playing a crucial, yet distinct, role. Firstly, we have the galaxies themselves. These are the shimmering jewels, the visible expressions of the cluster. They are what first draw our eye, what capture our imagination with their swirling arms, their luminous cores, their countless stars. Yet, in a beautiful paradox, these luminous galaxies, despite their brilliance, make up only a small fraction of the total mass of the cluster. They are the visible tip of an enormous, unseen iceberg. They are the only component we can directly detect in the visible spectrum, the light our eyes are attuned to. They are the familiar, yet they are but a small part of the story. Secondly, there is the heated gas of what we call the intracluster medium, or ICM. Imagine this as a cosmic ocean of extremely hot, diffuse plasma that pervades the space between the galaxies. Its peak temperature is astounding, soaring to between 30 and 100 million degrees Celsius. One might wonder, how can gas in the vast emptiness of space reach such temperatures? It's a testament to the energetic processes that occur within these immense structures. This gas is so hot that it emits X-rays, a form of light invisible to our eyes, but detectable by specialized telescopes. So, while we cannot see it with our naked eye, it whispers its presence to us through these high-energy emissions, filling the space between galaxies with a silent, fiery breath. It's a reminder that the empty space of the universe is rarely truly empty, but often filled with subtle, powerful energies. And thirdly, we come to the profound mystery, dark matter. This enigmatic substance makes up the vast majority of the mass of galaxy clusters. It is the silent architect, the invisible glue that holds these massive structures together. We cannot see it, we cannot feel it, it does not interact with light in any detectable way, hence its name. Yet, its gravitational influence is undeniable, its presence inferred from the way galaxies move within clusters, and from the way light bends around them. Dark matter is a humbling reminder of how much we still have to learn about our universe, how much lies hidden beyond our direct perception. It is the unseen hand, guiding the evolution of these magnificent structures, shaping the very cosmos in ways we are only just beginning to comprehend. Imagine an entire universe, mostly composed of something we cannot even touch or see. It's a thought that truly invites reflection, allowing our minds to wander into the realms of the unknown. Now let us gently turn our thoughts to the birth and life, the very formation and evolution, of these colossal entities. How do such grand structures come into being? It's a process of immense cosmic drama, a slow, majestic unfolding over billions of years. As galaxy clusters begin to form and grow, the universe performs a grand symphony of energy release. Massive amounts of energy are liberated, manifesting as powerful shock waves, the intense heating of gas, and the dynamic interactions between galaxies themselves. Picture vast currents of gas, flowing through the early universe, drawn together by the nascent gravitational wells of forming clusters. As this gas collides with existing material within the developing cluster, it generates these powerful shock waves. These aren't like sound waves in air, but vast ripples of energy, silently propagating through the cosmic medium. These shock waves are what drive the gas to those incredible temperatures of tens of millions of degrees, creating the X-ray emissions we spoke of earlier. So, the very heat that fills the intracluster medium is a fossil echo of the violent, energetic birth of these structures. It's a powerful reminder that while the cosmos often appears serene, its fundamental processes are dynamic and full of energy. Within the heart of a forming cluster, galaxies are not simply passive observers. They are active participants in a grand cosmic dance. Galaxy evolution within the cluster is profoundly governed by interactions between these stellar islands. Imagine two galaxies, each home to billions of stars, slowly drawing closer under the persistent pull of gravity. They might engage in a majestic, slow-motion ballet, eventually merging to form a single, larger galaxy. This isn't a sudden crash, but a gradual intermingling of stars, gas, and dust, playing out over hundreds of millions, even billions, of years. It's a process of cosmic alchemy, where two become one, forging new, more massive stellar cities. Alternatively, a galaxy might experience a process known as gas stripping. As it moves through the dense, hot intracluster medium, the pressure of this superheated gas can effectively strip away the galaxy's own supply of cold gas. This loss of gas can dramatically affect the galaxy's ability to form new stars, potentially leading it to become a red and dead galaxy, its stellar nurseries silenced, its vibrant star birth extinguished. So, within these clusters, galaxies are constantly being shaped, transformed, and redefined by their environment, a testament to the dynamic, ever-changing nature of the universe. Like any complex system, human beings have sought to classify and categorize galaxy clusters, to bring order and understanding to their immense diversity. There are many classification systems, each offering a different lens through which to view these cosmic structures. These systems are based on various characteristics, such as the cluster's overall shape symmetry, whether it appears smooth and round, or more elongated and irregular, its X-ray luminosity, which tells us about the amount and temperature of its hot gas, and the type of dominant galaxy found at its core. One such system is the Botz-Morgan classification, which sorts clusters into types 1, 2, and 3. This classification is based on the relative brightness of the brightest galaxy within the cluster compared to the other galaxies. A Type 1 CLU star, for instance, exhibits the greatest contrast, meaning it has one exceptionally bright, dominant central galaxy that stands out prominently. A Type 3 cluster, on the other hand, shows the least contrast, with many galaxies of similar brightness, perhaps indicating a more diffuse or less evolved structure. These classifications are not just labels, they are clues, whispers from the distant past, helping us to understand the different evolutionary paths these clusters may have taken. Beyond simply existing as magnificent structures, galaxy clusters also serve an incredible purpose. They act as measuring instruments for the universe itself. They are not just objects of study, but tools that allow us to probe the fundamental laws of physics and the very nature of space-time. One profound example of this is their use in testing predictions of general relativity, Einstein's groundbreaking theory of gravity. Let us gently consider the phenomenon known as gravitational redshift. Radek Wojtak, from the Niels Bohr Institute at the University of Copenhagen, utilized galaxy clusters to study a very specific prediction: the energy loss from light as it struggles to escape a gravitational field. Imagine a photon of light, a tiny packet of energy, being emitted from the very heart of a massive galaxy cluster. The gravitational pull here is immense, a profound well in the fabric of space-time. As this photon begins its long journey outwards, it must climb out of this deep gravitational well. In doing so, it loses energy. This isn't like a physical struggle, but a subtle, fundamental interaction predicted by general relativity. Now, imagine another photon emitted from the very edge of the same cluster, where the gravitational pull is much weaker. This photon has an easier ascent, losing less energy. What does this energy loss mean for the light we observe? When a photon loses energy, its wavelength stretches. It becomes redder. This effect is known as gravitational redshift. So, light emitted from the center of a cluster, where gravity is strongest, should have a longer wavelength, appear more redshifted, than light coming from the cluster's less gravitationally intense edge. Wojtak, with immense patience and meticulous work, gathered data from 800 galaxy clusters. Think of the sheer volume of information, the countless photons whispering their tales from across the cosmos. He was able to study the properties of gravitational redshift for the distribution of galaxies within these clusters. And what did he find? His observations beautifully confirmed Einstein's predictions. The light from the clusters was indeed redshifted in proportion to its distance from the center of the cluster, exactly as general relativity foretold. This remarkable result is more than just a confirmation of a theory. It is a profound validation of our understanding of gravity on the largest scales. And in an even deeper sense, it strongly supports the lambda-cold dark matter model of the universe. This prevailing model suggests that most of our cosmos is made up of that mysterious dark matter, a substance that does not interact with ordinary matter or light, but whose gravitational presence is undeniable. To see its subtle effects, validated by the bending of space-time itself, is truly a moment of cosmic revelation. It's like seeing the shadow of an invisible hand, subtly shaping the light of the universe. Beyond testing gravity's fundamental laws, galaxy clusters perform another spectacular service. They act as cosmic magnifying glasses, allowing us to peer into the universe's distant past. This phenomenon is called gravitational lensing. Because galaxy clusters possess such strong gravitational potential, their immense mass literally warps the fabric of spacetime around them. This warped spacetime then bends the path of photons, much like a conventional lens bends light, creating a natural, cosmic magnifying glass. Imagine light from an incredibly distant galaxy. Why, perhaps a galaxy so far away that its light left it when the universe was just a fraction of its current age. This light travels across billions of light years, only to encounter a massive galaxy cluster in its path. Instead of being completely blocked or merely passing by, the cluster's gravity gently, yet powerfully, bends and focuses this light, redirecting it towards our telescopes here on Earth. This incredible natural phenomenon allows us to observe these distant galaxies during their very early stages of formation and evolution, galaxies that would otherwise be far too faint and small to be detected by even our most powerful instruments. It is literally looking back in time, seeing the universe as it was billions of years ago, thanks to the intercession of these colossal clusters. It's like the universe providing us with a special set of glasses, allowing us to see details we never could before. This gravitational lensing can be observed with photons of any wavelength, from the visible light we see with our eyes to the high-energy X-ray band. While X-ray lensing can be more challenging to detect, as galaxy clusters themselves are strong emitters of X-rays, scientists can cleverly combine X-ray data with optical data to piece together the full picture. For instance, the majestic Phoenix galaxy cluster has been used in this way, allowing astronomers to observe a dwarf galaxy in its early, high-energy stages of star formation. Imagine seeing the very infancy of a tiny galaxy, amplified and brought into focus by the gravitational might of a giant cluster. It's a profound reminder of the interconnectedness of all things, how even the largest structures serve as windows to the smallest, and the most distant. As we gently bring our journey to a close tonight, let us contemplate some of the notable galaxy clusters, these silent giants that populate our cosmic neighborhood and the distant reaches of the universe. In the relatively nearby universe, within distances that we might metaphorically call our local galactic backyard, we find clusters like the Virgo cluster. This is our closest large cluster, and our own Milky Way galaxy is gravitationally influenced by it, part of a larger supercluster that includes Virgo. Then there's the Fornax cluster, a somewhat smaller but equally fascinating gathering. Further out, we encounter the majestic Hercules cluster and the truly immense Coma cluster, both renowned for their richness and the sheer number of galaxies they contain. These are our neighbors, relatively speaking, providing invaluable insights into the ongoing processes of cosmic evolution. But the universe holds even grander, more mysterious influences. There is a vast aggregation of galaxies known as the Great Attractor. This isn't a single cluster, but a region of space of immense mass, dominated by the Norma cluster. Its gravitational pull is so profound, so immense, that it is literally affecting the local expansion of the universe. Our entire local group of galaxies, including the Milky Way, is being subtly, yet undeniably, drawn towards this great attractor. It's a powerful, silent current in the cosmic ocean, a testament to the fact that even on the largest scales, gravity continues to shape and direct the flow of matter. And then, we peer back in time, to the distant, high redshift universe, to clusters that existed when the cosmos was young. Here, we find colossal structures like SPDCL J0546-5345 and SPDCL J2106-5844. These are some of the most massive galaxy clusters ever discovered in the early universe. To find such enormous structures existing so early in cosmic history challenges our understanding of how quickly such colossal entities could have assembled, painting a picture of a dynamic and rapidly evolving young universe. In recent decades, scientists have also discovered another fascinating aspect of galaxy clusters. They are relevant sites of particle acceleration. Imagine particles, fundamental compounds of matter, being accelerated to incredible energies within these clusters. This feature has been unveiled by observing non-thermal diffuse radio emissions, a form of light far beyond what our eyes can see, picked up by radio telescopes. These emissions manifest as vast, glowing structures known as radio halos and radio relics. These aren't the result of stars, but of powerful, non-thermal processes, perhaps related to the shock waves we discussed earlier, or the turbulence within the intracluster medium. These radio whispers tell us that galaxy clusters are not just static collections of galaxies, but incredibly dynamic, energetic environments, teeming with invisible activity, accelerating particles to speeds that challenge our imagination. Using instruments like the Chandra X-ray Observatory, scientists continue to unravel these hidden energies. And so, dear listener, we conclude our gentle journey through the realm of galaxy clusters. from their silent gravitational embrace of thousands of galaxies, to their hidden seas of superheated gas and the profound mystery of dark matter, these structures offer a window into the grand, unfolding story of the cosmos. They are laboratories for testing Einstein's relativity, cosmic magnifying glasses for peering into the universe's youth, and silent witnesses to powerful, unseen energies. As you drift towards sleep, perhaps you can carry with you a sense of the immense scale, the quiet power, and the profound beauty of these cosmic gatherings. Remember the silent dance of gravity, the unseen influence of dark matter, and the distant whispers of light from across billions of years. Let these thoughts bring a sense of perspective, a calming understanding of our small, yet significant, place within this magnificent universe. May your dreams be filled with the quiet wonder of the cosmos. Good night.